Friends, a frame structure is nothing but a structure made out of by only line elements or line members. So, if you take a line, it consists of a horizontal axis like this. So, along this horizontal axis or axis of the member, the dimension is very large when compared to the cross-sectional dimensions. So that's why it is called as a line member. So the cross-sectional dimensions are small when compared to linear dimension. And this dimension along the axis of the member is called the length of the member. This is axis of the member. So now let us define what is meant by a local coordinate system, local coordinate system and global coordinate system, global coordinate system. So if you take a line member like this, so the axis itself is chosen as one of the coordinate axes. This axis of the member itself we choose as one of the axes, and that is called the horizontal axis. In the local coordinate system, we select the axis of the member itself, one of the coordinate axes, general coordinate axis for specifying displacements, force, load, everything, whatever it is. And the other two axes which are normal to this, one like this, another normal perpendicular to this. So these two axes which are normal to this general axis of the member, we call it as the other two coordinate system. This sort of coordinate axis we call it as local coordinate system. Local coordinate system is nothing but choosing the axis of the member itself as one of the coordinate axes and other two normal to it as other two axes. Whereas the global coordinate system, always already, we select the horizontal axis as the x-axis and other two normal to this, we call it as the other two coordinate system, xx, ys, and z system. That is the definition of local and global coordinate system. Why we have to define this coordinate system is always the load or displacement, it can occur in any direction in space. But for analysis purpose, always we resolve them into these three fundamental directions. The three fundamental directions to which we resolve, they can be either pertaining to local coordinate system or global coordinate system. Because some of the basic fundamental properties of the elements or members which the structure has been made out of, it is easy to define with respect to the member axis. So we select the member properties we determine with respect to this local coordinate system, then we transfer them to the global system. Generally, the external loads will be acting pertaining to global coordinate system. We define the external loads acting on the system with respect to always global coordinate system. So the effect of that with respect to member axis, we have to determine through what is known as transformation matrices. So that is the actual definition of the two system of coordinates. One local coordinate system, or it is also called as member coordinate system, member coordinate system, or a global coordinate system or system axis. global axis or system axis. These are the two types of systems which, with reference to which we define all our loads, displacements, and also stresses, everything. Because they are all vector quantities, we need a definite direction to indicate their action. So that is why, with respect to these two coordinate systems, we define their direction. That is one important basic concept one should have in mind. Then we have to find out the relationship between this local system and global system, or we have to interrelate the analysis results with respect to local coordinate system to global coordinate system, or vice versa, through what is known as rotation transformation matrix or rotation transformation matrix, using what is known as principle of contrariety. That I will take up a little bit later. So one thing you have to remember is this coordinate system. So then, as I told you, all the properties we define with respect to these material properties. All the material and geometrical properties, all the material and geometrical properties. Geometrical properties means your area of the moment of inertia, all these things, or section modulus, all these things will be defined with respect to local coordinate system. Your moment of inertia about x, y axis with respect to local coordinate system only be defined. Likewise, the area of cross section also with respect to your local coordinate system, width and depth, they are all going to be defined only with respect to local coordinate system. So all the material and geometrical properties along with this stiffness and flexibility, they are also inherent property associated with the element or member of the structure, and they are also defined only with respect to these local coordinate system. That is, all the material and geometrical properties along with stiffness and flexibility. Stiffness and flexibility are defined with respect to local coordinate system. Local coordinate system. Generally, any member, it is going to be defined as the element, any element or member of a structure. It has two ends. One is I end, another j end, or this you call it as j end, k end, element as I. Or element you can call it as E, and one end as I, another end as j. This is left end, that is right end. Always we have to define the left hand and right hand of the members correctly in our analysis. Why this is very, very important, the left hand, right hand? Because it defines the direction of this local coordinate system. Always the local x-axis lies from left hand to right hand. So left hand we have to define correctly, which is our left hand. So in any member, one end is always called as the left end, and generally the length is measured from that particular end. All the displacements, especially in flexibility concept, we define what is known as relative displacement. Relative displacement means the net displacement with respect to one of the ends. So we treat one end as stationary only with reference to that end. The displacement of force from the other end will be defined. That is why this end, for all practical purposes, you can treat it as the origin of the axis. The origin of the local coordinate system always lies at I end, that is left end. That's why always for any member we have to define the two ends, which is the left end or starting end. That correctly we have to define. If we define this as the left hand. Then of course the sign will be reversed because these are all vector quantities, force, displacement. Sign is very important. Always we have to define the origin only from the left hand and clearly indicate. Of course there is no rule. Always this particular hand has to be treated as left hand. So there is flexibility. Either this also you can choose as left hand. But only thing is you should continue with that particular thing throughout your analysis. Otherwise this sign gets different or mixed up. So that is why this particular system of coordinates is very important. The moment I told local coordinate system, member axis is chosen as one of the coordinate axes and always left hand is chosen as the origin. Even right hand also can be chosen as origin. There is no actually restriction. There is no bar. You can choose the other end also this as the origin. So it all depends that you have to clearly indicate in your before the analysis which is Jn or Yn, which is Jn of the member. Or member itself we can indicate it by Ij, that is always the first letter indicates the origin or left hand. We have to say member 1, 2. Or if you say 2, 1, 2 will be the origin. So all that type of sign convention also can be used during our analysis. This much point you have to clearly remember in this coordinate systems, local and global coordinate system during the analysis of the members of a framed structure. Framed structure means it can be continuous frame, it can be truss, it can be rigid plane frame. Out of that, any member, which are all line members, so you have to be very, very careful that line members, it will have two ends and the two ends should be correctly, clearly defined from which end to which end the axis runs. That you have to clearly indicate during your analysis. This point is a very important thing that one has to note down. I hope I made the point very clear. Local and global coordinate system, especially the local system with respect to the member, because there only we define all the geometrical properties and material properties and also this flexibility, stiffness. We define only with reference to the local coordinate system, and local coordinate system has to be clearly defined. So after this, the next point we will come to this load deformation relationship. Load deflection or deformation. Load deformation relation. So this is another concept which before going for defining stiffness and flexibility, so this concept of load deformation is another important thing which we have to remember. Already instead of materials, you have conducted the experiments, tension test and compression test like that, and you have plotted the load and also the deformation. Deformation either tension or compression, and you have plotted the time and you have observed up to certain portion the load is proportional to displacement. Generally, we plot the deformation along horizontal axis and load along vertical axis. Load deformation. So here, all our analysis we are defining or we are doing only well within the elastic domain. That is, beyond the elastic domain, we don't do any matrix analysis by this flexibility and stiffness method. So, within the elastic domain means the load deformation relationship is always linear. So, that's another important concept you have to remember. That is, load is directly proportional to deformation. Whatever the amount of variation is there, either with respect to load or with respect to deformation. Same, if one is varied by certain amount, the other also corresponding to that, it will vary by same amount. That is this definition of linear variation. One is directly proportional to another. That is, this load P is directly proportional to displacement, or you can say deflection is directly proportional, or deformation is directly proportional to load. That is within elastic limit. Within elastic limit, this load is proportional to displacement. That is, and this is another thing. And remember, always all our analysis we do within the linear elastic domain. And also another thing that remember is what is known as principle of superposition. Principle of superposition. This already I have mentioned in the earlier lecture. Here I will explain what is the principle of superposition. Suppose you have a structure which is subjected to two systems of loading, say P1 and P2, resulting in a deformation of delta 1 and delta 2. So when a system of load like this P1, P2, P3, etc., resulting in some type of deformations, then the effect of this, when all of them are acting, whatever the displacement you are going to get, that will be same as the sum of the individually, if you consider each one of them acting separately and added. That means the effect of displacement delta will be delta of 1 plus delta of 2. This delta 1, 2. So the combined effect of number of loads will be equal to the sum of the effect of loads which are acting independently. That principle is called principle of superposition. Suppose if you have a number of loadings resulting in a certain displacement at different points, and that displacement will be same as if you take one load acting independently and finding the displacement at all those points, and then if you add it, you will get that same displacement as what you are going to get as if everybody, all the other loads are also acting. That is called the principle of superposition. That means suppose if a load P1 results in a displacement delta 1, another P2 resulting in displacement of delta 2. So that means this net displacement, when both of them are acting, will be same as if you take P1 and measure the displacement individually, then again apply P2 and measure the displacement, add it together, that is delta 1 plus delta 2. That will be same as if you combine the effect of that. That is called the principle of superposition. I hope I made this clear. This superposition principle will be hold good only when this load deformation curve is linear. That's another important thing you have to remember. When the load deformation curve is linear, then only this principle of superposition is valid. Otherwise, the principle of superposition is not valid. Beyond that, linear variation, this law of principle superposition is not being valid. So, in such situations, with these two, when principle of superposition holds good as well as within linear elastic domain, you can always say P is proportional to D or vice versa. D is proportional to P. You can always conclude this. Then this equation, you can call it as P is equal to some constant into D. Likewise, this also you can call it as D equals some constant into P. Because it is linear variation, y is equal to mx form. This also y equals mx form. Linear variation, naturally the relationship between load and deformation is through this constant. Here also deformation and load relationship is through a constant quantity. So this constant what we have is called stiffness and this is called flexibility. They are the basic property associated with the material of the element or member of the structure. So where you are going to define, call this K as stiffness and this F you are calling it as flexibility. There is nothing much here. This is the basic concept of stiffness and flexibility. Within the elastic domain, where law, principle of superposition holds good, you can always conclude load proportional to displacement or vice versa, D proportional to force. Or you can relate them by a constant quantity. Load is related to displacement by stiffness or displacement is related to load by another constant and that constant we call it as stiffness and flexibility. Here, this stiffness and flexibility they are converse to each other. Flexibility is converse of stiffness because this P is proportional to D, that is D is proportional to A. One is converse of the other. So always this stiffness is converse, flexibility is converse of stiffness or vice versa. Flexibility is converse of stiffness. So from this basic equation, I will call this as 1, this as 2. Suppose if D is equal to 1, then K is equal to P. This helps me in defining what is stiffness. From this obvious, suppose if D is equal to 1, K equals P. P is equal to Kr. That means this stiffness I can define as the force developed due to unit displacement. That's as simple as that. I will define now the stiffness as a force developed due to unit displacement. You give a unit displacement, see what is to give that unit displacement. Then if you give it, what is the force developed or what is the force required to develop that unit displacement we define as stiffness. Likewise, here also if P is equal to 1, then F is D. That is, if the displacement developed due to unit force, that is defined as flexibility. I hope I made the point clear. So, K equals P. That is, stiffness is defined as the force due to unit displacement. Likewise, here flexibility is defined as force and displacement is defined as displacement due to unit force. It is displacement due to unit force. Here it is the force due to unit displacement. This is the actual definition of stiffness and flexibility. So the important points to be remembered are one-dimensional structure, its coordinate system, local coordinate system. Only with respect to that only we define all these: stiffness, flexibility, or force, displacement occurring. Because force and displacement vectors, we need to define the direction, and that direction, how we define, is always with respect to local coordinate system. And the load deflection, which are vector quantities, they will be giving a linear relationship within the elastic limit, and all where local principle of superposition is valid, so we can define is stiffness and flexibility, the fundamental properties of the material associated with all members of the structure, which helps us in doing the analysis. This is the basic concept. And here I define stiffness and flexibility only due to a unit force, due to one force and one displacement, resulting one displacement. But in actual practice, we get a system of forces giving system of displacement. So the effect of all those, we can apply principle of superposition by considering each of them acting separately and knowing stiffness and flexibility, we can match the effect together. So this is the basic concept which we use in our analysis. And if you have a number of systems, for all those systems itself, you can define what is meant by stiffness matrix and flexibility matrix. We use the term matrix because we are dealing with group of loads or system of loads resulting in system of displacements. When you are terming defining certain terminologies with respect to a group, so that the entire group you can arrange them in matrix form, and accordingly we define the properties also. So we can define what is meant by a stiffness matrix and flexibility matrix for group of or number of system of forces and system of displacement, that is matrix notation. Right? So now we actually define what is stiffness matrix and flexibility matrix for elements of our frame structure, plane frame structure. Because in the beginning itself I told we are dealing with analysis of plane frame structures only and not two-dimensional or three-dimensional structures. For these plane frame structures like beams, trusses, grids, or rigid plane frames or rigid space frames, for all these you can define what is the stiffness matrix and flexibility matrix. That is the elements or members of all these structures, grid structure, truss structure, space structures, whatever it is, that for those structures we define the member or element stiffness matrix and element flexibility matrix. That is our next subject matter. So we define this stiffness matrix and flexibility matrix with respect to members or elements of the structure. That elements are members of the structure as a whole. That structure means either it may be a simple plane frame structure, a plane truss structure, or it may be a space, say, element or member of a space truss structure, or a continuous beam structure, or a space plane structure. Now let us define what is meant by element stiffness matrix. Element stiffness matrix. or KME, either way you can define. I would say KM itself, element stiffness matrix. First, I will take this. Consider a simple bar or spring. Element with 1 degree of freedom. So this already I have defined. Degree of freedom means it is always kinematic indeterminacy. Degree of freedom, whatever the type of displacements or which are now occurring at the ends of the members, so we define degrees of freedom, number of independent displacements. So consider a bar element with 1 degree of freedom. That means if you take a bar element, bar is simple line element, so your coordinate system, local coordinate system will be like this. This is local or member x-axis and this is local member y-axis, and of course z-axis will be normal to the plane because this is planar structures we are dealing with. So these two are planar axis or planar orthogonal axis. Other orthogonal axis will be normal to the plane, either outside the plane of the board or inside the plane of the board. That is your another local axis. So you consider a bar element of length L and axial rigidity AE. Area of cross section is A and the Young's modulus of elasticity of the material is AE. So the product AE we call it as the axial rigidity. The two ends I will call it as one end as 1, another end as 2. So or this is I, this is Jn. So this is element E. Any member element E. Or this you call it as I, this Jn, Kn. Generally in your programming, when we are doing the analysis using computers, we always call this I notation as for member. I equals 1 to m number of members. Jn as left end, that is usually the origin, Kn as the other end, the two ends, because we are dealing with only line elements which has two ends, always left end, we can call it as Jn, right end, we can call it as Kn, this is usually the origin, this as the member, I. These are nodes or ends, this big square bracket or I, any member or element or either element E or I member. So with having two ends, of length L, A axial rigidity with 1 degree of freedom. Generally, though it will have a number of points, infinite number of points, we don't deal with all the points, we deal only generally the end points which we call it as the nodes, and knowing the properties at the ends, we can interpolate what is the value at all other intermediate points. So during our analysis, we determine the unknowns only at the end points, that is Jn and Kn. Though there are number of points, strictly speaking, at all the points, we have to find out the required values of stresses, displacements, whatever it is. We don't, during an analysis, we don't determine at all those points. Strictly speaking, first we determine at the end points, then we can determine that. All the unknowns we determine at the ends, then we can plot bending moment diagram or shear force diagram, which represent the value of bending moment or shear force, that internal stresses at all other points. So only we determine the values at the ends. So here degrees of freedom is the displacements only at the end points. Generally we take the positive direction along with the coordinate system like that. So this is the one displacement, a displacement at 2, which you can call it as the displacement as at 1, and positive direction is left to right always, that is considered as positive. That's another thing which is important, sign convention. Always we take from left to right positive direct forces, then similarly all the forces from bottom to top positive, and the rotation in clockwise sense we take it as positive. This is the sign convention we normally adopt because we are dealing with only maximum 3 degrees of freedom, because we are dealing with analysis of plane or planar frame structures. So planar structures will have only 3 possible degrees of freedom at any end. So here I am considering only 1 degree of freedom. So other 2 will be the other, vertical and the rotation. So we consider 2 degrees of freedom like this. So then, and forces. Of course, this is always we talk about displacements only first. Then the corresponding forces, here we can call the force as P2. Here we can call the force as P1. So here always we define the stiffness matrix. Stiffness, I will give you the definition of stiffness matrix. Stiffness matrix of an element is defined as the relationship between the independent is defined as the relationship between the independent displacements at the 2 ends and the forces and the corresponding forces at the ends, which may or may not be independent. So that is how I define the stiffness matrix. Of course, stiffness matrix pertain to one quantity, either one force and one displacement. Already I have defined. So the stiffness I have defined as the force required for unit displacement. But here I am considering the system of forces and displacements. The moment I consider line element, always it will have 2 ends. At 2 ends only we consider force and displacement, possible force and displacement. Here I am considering a case of only a body element wherein it will have only one force resulting in one displacement at one end. So there are 2. Like that, if you have all the 3 are there, means 3 here, 3 other here. So 6. Like that, when you have a system of forces, system of displacements, I told you already, we define what is known as stiffness matrix and flexibility matrix. So it consists of the system of forces and system of displacement. Again, I am defining altogether in a different fashion. I define the stiffness matrix as it is nothing but a relationship between independent displacements and the at the end with the forces, corresponding forces causing those displacements. The forces can be either dependent and independent or may not be independent. Generally, it will not be independent. Whereas displacements, it it will definitely be independent. So that's why I have considered here by defining stiffness, independent displacement I have to. So in displacements U1 and U2 are independent. Here, forces need not be independent because to satisfy equilibrium condition, because always I told you we have to satisfy the conditions of equilibrium, which I told in the very first class. Before all our analysis, structure has to be equilibrium or stationary condition. We don't allow structure to be unstable or not stationary condition. So to satisfy equilibrium condition, you know, sigma f has to be 0. That means f1 plus p1 plus p2 is 0. So our p1 equals minus p2. That means the forces, they are not independent. P1 is nothing but equal and opposite to P2. That's why I made this statement. So very important, clearly what the moment I told define the stiffness matrix, it is nothing but the relationship between independent displacements with the corresponding forces. Forces, it need not be independent. Only displacements can be independent. Forces need not be dependent. That's another thing you have to remember in this particular, while dividing the stiffness. So these are the key points which you have to remember. I have considered a body element with only simple 1 degree of freedom, one displacement at the two ends, U1 and U2, the corresponding forces P1 and P2 at the two ends, and here U1, U2 will be independent and P1, P2 need not be independent because it has to satisfy the equilibrium requirement always. So this evidently it concludes that forces are not dependent. So we have to consider only the net displacement, because there is only one force is the unknown, right? So there are two independent displacements, but one force is the unknown. Here displacement may be 0, here you may have displacement. But force, definitely they are different, it will be there, and one depends on the other. Right? Always it is not independent. That's why I told you, a net displacement only I will consider instead of 2. The net displacement will be U2 minus U1. So this net displacement, I will call it as delta. So when you have displacement, therefore strain is equal to U2 minus U1 divided by L. Strain we define as the change in displacement divided by original length. Length I have taken as L. Strain is this change displacement, net displacement divided by L. Therefore, stress is equal to U2 minus U1 divided by L into area. Not area, it is V. Because they are working within the elastic domain, stress is proportional to strain like load and deflection. Therefore, it is linear relationship, sigma is proportional to epsilon, therefore sigma is equal to E epsilon, therefore sigma is equal to E times epsilon, that is E times strain. This is actual net displacement, this is strain, that is displacement divided by original length. Stress is this strain into G. Therefore, force, unknown force, that unknown force is P2 is nothing but area of cross section I have taken as A into the stress. I multiply by area of cross section because force is nothing but stress into area of cross section. So AE by L U2 minus U1. And of course, your P1 is nothing but minus P2 from equilibrium condition. Therefore, now you can relate the forces in matrix form in matrix form. In matrix form, the force displacement, relationship of the element I. You can write it as P1 P2 equal to E by L 1 minus 1 minus 1 It is said that equation I write it in matrix form because now you can see P1 is nothing but A by L minus U1 minus U2. P1 equals A by L U1 minus U2. Here I told P1 equals minus P2. That means P1 is minus A by L U2 minus U1 or it is U1 minus U2. Likewise, P2 equals A by L minus U1 plus U2. That's what exactly you got here. So this is the matrix form of whatever I did here. It is mainly basic. So now I define here stiffness matrix of an element is defined as a relationship between independent displacements and the corresponding forces, which need not be dependent. That's independent. So this is the relationship joining them together. So this we call it as a stiffness matrix of this bar element. It is very simple thing. Nothing that whatever we have studied in strength of materials and the kinematic indeterminacy and all those things, whatever I just defined in my lecture, that is principle of superposition, linear elastic domain, basic concepts only. Using that, now I have defined the element stiffness matrix for a bar element, simple bar element. Like that, simple plain truss element, simple beam element, simple rigid plane frame element, space stress element, we can derive a relationship like this. That is called stiffness, member stiffness matrix or element stiffness matrix. That's a property associated only with the elements. Then our loads are all in global direction, we relate them. So that is the basic concept of our matrix structural analysis. Because we always deal with number of forces resulting number of displacement, we resort to matrix notation as I have used. Because earlier I defined simple stiffness flexibility by one quantity. I defined that holds good. But when you have group of number of forces, number of displacement, then always we have to resort to matrix notation and we define the properties with matrix. So this you can call it as a P matrix. This is a displacement matrix. This is the member stiffness matrix. So therefore, your member stiffness matrix of a bar element is bar or even plane truss or space truss. Plane truss, space truss, because already I told while defining kinematic indeterminacy, a truss element always will have only one internal force or one internal stress. That's why you don't, the degree of indeterminacy is m, internal indeterminacy is m into 1. Then plus r, that is number of reactions. So m plus r are the unknown to be determined during the analysis. So here, even plane truss or space truss element is similar to bar or spring element. If you take a spring element, then also it is same thing. The two ends, same forces. Spring, bar, plane frame element, space frame element. All this is dependent by our element stiffness matrix. If they ask you to derive the element stiffness matrix for a plane truss element or a space truss element, this is what you have to do. Consider, as here I have told, consider simple bar element. You change that to consider a simple truss element, plane truss element. Consider a simple space truss element with respect to local coordinate system that you have to mention. All the things which I am using terminologies, they are very, very important. Local system, I told, the member axis is chosen as one of the axes. With reference to that only we consider our unknowns, displacements, forces, vector quantities, their magnitudes, numbers, that thing. Same thing also. So this element stiffness matrix now I have defined. This is called element stiffness matrix. This you have to remember. Element stiffness matrix for bar, a spring, bar, plane frame, a plane truss, or even space truss. The element stiffness matrix. I am not talking about global. Global is a different thing. For plane stress it is two-dimensional thing. For space stress it is three. That you have to be careful. That we will take up when we talk about problems. We work problems of plane stress, space stress. But for bar and spring, this we can straight away use. For plane truss and space truss analysis, I have to again define the stiffness matrix with respect to global coordinate system only. Whereas for bar element and spring element, the local and global coordinates, they are one and the same. That's a very, very important note that if you take bar element, this is local coordinate system, global, it again you can take it. Global and local coordinate system, they are one and the same for both bar and spring element. But plane frame and space stresses, though this stiffness matrix, which I told same with respect to local coordinate system, but for global it is different. That's why we have to derive the global stiffness matrix there and do the analysis separately. But spring and bar, only this. Local and global, absolutely there is no change. You can do analysis of bars or springs, which is given a number of spring elements attached like this. One spring, another spring, another spring, right, subjected to a load. Fixed at one end. They may ask you to find what is the net extension, total displacement. So then give all these values, thicknesses. Then we can use this. Local and global coordinate systems are same. We can do analysis using only this Km value. Likewise, even bar problems like this, step bars, like that, subjected to a load. What is the net extension? Or what are the forces at various points? This also we can do by using the same stiffness matrix. All these problems. So I'll give a set of exercise by doing the problem. I'll give you. You can use the ready-made programs, right, for analysis of springs and bars, and you can get the solution. First, do it by hand computation. Find element stiffness matrix of this, element stiffness matrix of this, because here you have 1 degree of freedom, another degree of freedom, 2, here another degree of freedom, 1, 2, 3, all the same direction. You find here, of course, one more, 1, 2, 3, 4 degrees of freedom. For this element, you write the stiffness matrix with 1 and 2 as the degrees of freedom. Here I told U1, U2. There you can use 1 and 2. Then for this element, 2, 3. For this, 3, 4. Then you add all those things. That will be the total structure stiffness matrix. Likewise, total load matrix corresponding to this. Then use that relationship. P is equal to Km. This K, total structure altogether, because your principle of superposition holds good. I told principle of superposition is valid. We can add the effects of displacements and forces, which I showed by the graph, together. The effect of one load, another load, we can add it, all put together acting. Here put together acting, individually we can consider them as element bit by bit. I can add it together by applying principle of superposition. We can find the displacement. Here also, or even if it is a tapered section, like that. This we can divide it into number of sections of equal area, stepped like this, and do the approximate analysis of the tapered bar. All these tapered bars, stepped bars are springs. So there is no difference between local and global coordinate system. They are one and the same. So you can use the element as well as the global stiffness matrix are all same and finish the analysis. So next, when I take up actual problems, analysis of bars and springs, we can, I will tell it in detail. I'll take one example and work it and show how to do the analysis. But in plane stresses, it is different because local axis, global axis, because if you take the plane stress member, which may be, need not be horizontal or vertical truly. It may be inclined. So your local axis will be along the axis, but our global axis will be x and y, they are different. Whereas the spring or bar, they are coinciding. Only one axis, it coincides with the global itself. There, global and local are not coinciding. Even space stress or even when though the element stiffness matrix is same, global will be different. That I will derive. But later, we will be defining what is known as principle of contability, and you can derive this matrix. Now, we will take up the beam problem. How to derive this stiffness matrix or a beam element, beam member. That will be same for plane frame also, even for grid also. Only degrees of freedom will be different. In the case of grid, there will be two moments and one shear. Whereas in the case of rigid plane frame, there will be two displacements, translations and one rotation. So only degrees of freedom, maximum 3 in all these cases. They are all planar structures. Grids, rigid plane frame, beam, plane truss. Only space stress is a space structure. Of course, it is beyond this syllabus. Only planar structures, maximum 3. So that take together all the 3 degrees of freedom, whether it coincides with local axis or global axis. You see, if they coincide local axis, you need not have to bother. Analysis becomes very, very simple. As I told you here, in bar and spring, you can finish off the analysis. Now I have completed the definition of the member stiffness matrix. I have derived the member stiffness matrix for all beam and on the spring, bar, planes in a truss, space truss elements. This is the member stiffness matrix. You see here it's a function of only area of cross section, chemical property, E, material property, L, again a material property. And this is also property, basic property associated with the element, inherent property. So this inherent property is a very, very important concept which one should have. The knowledge of this is very, very important on doing the analysis or for finding out the response of the structure. That is internal stress development and displacement determination. So that is that. So now we will take a bar element. I hope I made the things clear. Now we will take up element stiffness matrix for a bar element, not bar element, beam element, which is 20. Also, stiffness matrix for beam. Beam. Now I have derived for plane frames, plane truss, space truss, bar and spring. This, you have to remember, this is the element stiffness matrix. I am talking about only stiffness matrix. Next I will take a flexibility. Because stiffness is very important because as I defined there, displacements are independent. This is the relationship between the independent quantities, displacement and forces. Forces need not be independent, right? So that's why, since this is directly associated with the displacements, unknown displacements, so I am spending time on this. And this is a generalized procedure which is basically used in all analysis of structures. Whereas flexibility method, it has some limitations because it is force oriented and forces are not always independent. One depends on the other. It is very difficult to determine the unknown itself. When it becomes difficult to determine the unknown itself, which to be selected, which are the unknown, then it is definitely a difficult task for the analysis. So this stiffness method is the one which is widely used in the analysis. That is the reason that also have indicated why we go for only stiffness method. Because it is always deal with unknown displacements which are mainly independent in nature. It gives a relationship, forces can be easily done. There are flexibility, it depends on the unknown forces, but unknown forces need not be independent always. So it becomes very difficult. Which are the one which are independent? That selection itself, it becomes a tricky issue. So that is why this is widely useful. So I have told advantages also here itself, stiffness method and flexibility. Now we will take up beam element. Of course, it's also very, very simple. It is a one-dimensional element. So this is the axis of the beam. Here beam also, it may be either perfectly horizontal, perfectly vertical, or it may be inclined also. So naturally, local and global will definitely play an important role. Likewise, load also, it need not be along gravity type direction. It can be inclined also, it can be in any direction. So naturally, in beam, rigid plane frame also, which is basically made out of number of beam elements, rigid plane frame. So naturally, we talk about the global and local coordinate system separately, and whatever stiffness matrix I am talking about, I have to define both with respect to the element as well as global. Both we have to talk, and both knowledge we should have, and then only start doing the analysis. Now we consider a beam element, consider a beam element 1, 2, or beam element I. having J, J. These are very important things. Of course, I will just skip all those things. I hope that you have understood all those. So consider a beam element 1, 2 with 2 degrees of freedom at each end, as in figure. So, which are the 2 degrees of freedom? Of course, we assume beam to be axially rigid, right? So, it is rigid body motion equivalent. We assume beam to be axially rigid. If it is not axially rigid, for that time, number element stiffness for axial force similar to bar, you can take it, the same stiffness, attach it to the as 1 degree of freedom, right? So that is for axial forces only. That's independent, axial force. It is spring, bar, even for beam, though I don't consider here, right? So that you can add it to this element if it is not axially rigid. Now I have consider axially rigid beam. Consider axially rigid beam element with 2 degrees of freedom. So that means I will consider only these 2 degrees of freedom. 1, 2. I will number like that. First I will number rotations into 2 ends, then I will number. Or you can number continuously. Only that elements get integrated. There is no problem at all. Only 2. 1, 2. So I have this. I already told left hand starting from origin, you can go. Or vice versa. So there is no problem at all. Same thing goes good. Whereas here, the term, the elements will get changed. That's all. These are 2 different number of systems. You call this as 1, this 2, 3, 4. You can do it. There is no or there is no restriction. So for convenient purpose, I will take first rotation, then shear in a different way. So you can call length of the beam as L and the flexural rigidity as EI. The beam is basically under resisting loads by undergoing what is known as flexion and shear. Whereas other earlier one that was resisted by undergoing either axial tension or axial compression. Now I am considering an element wherein resistance will be in the form of flexion. It's a flexion member, not axial force member. Flexion member I consider where moment is there as well as shear force is there. This is what I consider. So with 2 degrees of freedom like this at each end. With 2 degrees of freedom at each end. So one end, 2, another end, 2. So totally 4. Right? So your stiffness matrix size will be 4 by 4. Whereas here there are 2 degrees of freedom, stiffness matrix size is 2 by 2. This degrees of freedom will give you the size of your stiffness matrix. Because first I defined stiffness, flexibility, force in proportion to displacement, or like that I defined. There it is only with respect to one number. Here now I am dealing with system, where you have different things. Naturally you are, that's why we use matrix notation. Nothing other than that. There is no other code. The group or number of things, when it is more than one, you have to arrange all of them in a group in the matrix form. That is matrix notation. That's how this matrix analysis has given birth. That is other than that. Analysis also very simple using MATLAB programs, you can do it. Each of them you can treat it as one unit only. As you are doing by hand computation, you can do by matrix notation, addition, subtraction, everything using that MATLAB. Anyway, you are doing that exercise using all these problems by that. So now I am deriving element stiffness matrix For beam element, this beam element I consider naturally the local axis will be the axis like this, 1 to 2. This is my local axis, local coordinate axis system. With respect to this system only, I will derive this. Right? Simple I will do. So here the displacements I will call it as theta 2. This displacement I will call it as V2. This is indicated by another sketch. 1, 2, the displacements V1. Always I will take positive direction of vertical displacement in the vertical direction of rotation clockwise, always positive, which I told already. The notation to be considered. Here it is V1, here it is theta 1, this is theta. So these are the displacements, unknown displacements. The corresponding forces, and this is the force M1, because force causing rotation is a moment. Here, this translation is a force. I will call it as Q1. This is V2, sorry. This is Q2, this is M2. These are all the forces. These are all the corresponding displacements. Right? So degrees of freedom, kinematic degrees of freedom are V1, theta 1, V2, theta 2. Corresponding static indeterminacies are M1, Q1, M2, M2. Q is shear, M is moment. So now I will use the well-known flow deflection equation, which you are already aware, for determining these difference matters. Right? So we will make things very simple. So we know, first before that, you can say, we know from equilibrium conditions, equilibrium requirement. First we apply equilibrium and compatibility conditions. From equilibrium conditions, so Q1 plus Q2 equals 0, or Q1 equals minus Q2. Correct? Here, that means though Q1 and Q2 have identified here as different, they are not independent. They are dependent. One, if you determine, that's enough. Other one, automatically, you can say it is equal and opposite. And also, you can say, if I take moment above 1, I can determine Q2. If I take moment above 1, I will get M1 plus M2, right? M2, M1, Q2 into L. So therefore, this Q2 equals M1 plus M2 minus. By simple equilibrium conditions, sigma V equals 0, sigma M about 1 equals 0. Right? So that means here Q1, Q2 you can determine, or Q1 vice versa, Q1 also you can determine. That means there are 4 forces. Out of that 4 forces, 2 forces cannot be independent. If you determine Q1, Q2 will be the unknown. If you determine Q2, then Q1 will be the unknown. Right? But either Q1 or Q2, we can determine by M1 and 2. So out of 4 forces, only 2 are independent. Very, very important concept. Right? Similar to bar. Though there are 2 forces, 1 is the only independent one. Whereas here, out of 4, only 2 are independent and the remaining 2 you can determine them. So here I can select either M1, M2 as the unknown, or I can choose Q2, M2 as the unknown, only 2 unknowns, Q1, Q2, M2, or Q1, M1, or M1, M2. There are 3 possibilities. Which to select? That's the dilemma now. Either I can choose anyone, because they are not independent, they are dependent on other. So all are not unknowns, only 2 are basic independent unknowns. Of that, again I am defined by talking about flexibility matrix. Now I am dealing with only stiffness matrix. So in stiffness matrix, it is displacements, all the 4 displacements, E1, theta 1, V2, theta 2, you can treat it. Because there is no equilibrium requirement doesn't say, which is independent. All are treated as independent. Versus someone. That's why I told you repeatedly, stiffness is the best suited one. Here the dilemma will come, which to select. Any selection can be made. So what I will do here, let us choose M1 and M2 as independent forces. I will use the general term force. Even for a moment also use the term force. So you can select Q1, M2 also, or Q1, M1 also you can select. Generally I will choose M1, M2 as independent. Why I am choosing M1, M2 means this moment is about z-axis, right? That z-axis is same even for local axis also. The global z and local z, they are one and the same. I need not have to bother. That is the reason I am selecting only the moments as the unknowns. If I select this V2, then actually global V2 and this is not the same. Because if this beam is inclined, then global V is occurred. Whereas in this case, we may have taken horizontal, global horizontal coincidence. That's okay. But generally it need not be in all cases. So local, global. Whereas rotation is always local, global. It is same for all planar structures. The axis normal to the plane, they are same for member as well as global. That's the reason I am selecting M1, M2 as independent forces. Okay? So we know from flow, deflection, equations which already you know at undergraduate level. So the moment M1, that is the MAB, is equal to 2dA by L into 2 theta 1 plus theta 2 plus 3 V2 minus V1 divided by L, 3 delta by L. Delta is net displacement, because this displacement you can take it in this fashion, right? The displacement, this is the rotation, theta 1, this is the rotation clockwise, theta 2 positive, and original direction is straight. This has moved to V2, then 2, it has moved here, then 1, it has moved here. This V2 minus V1 is nothing but the relative displacement delta. V2 minus V1. So that is 3 delta by L. That is your standard slope deflection equation. MAB is 2A by L into 2 theta A, theta B, 3 delta by L. Of course, the delta is also positive because this card rotation, which was tried earlier, now it is like this. That's anti-clockwise rotation. So your sway is positive. That's why I have taken as all positive directions will have taken this sign convention already you know in undergraduate level. So this is the basic stroke deflection equation. Like that, M2 also we can write it 2dl by L theta 1 plus theta 2 plus dv2 minus v1 by L. And here I have told Q2, which is M1 plus M2 by L from equilibrium requirement. So M1 plus M2 divided by L, which I can write it as 2I by L square, M1 by 2, and these two I will add it and get 3 theta 1 plus 3 theta 2 plus 6 v2 minus v1 divided by L. And of course, Q1 is nothing but minus Q2. Q1 is minus Q2. So this is minus 2 by L square into 3 theta 1 plus 3 theta 2 plus 6 v2 minus v1 divided by L. So I got the relationship between forces and displacement like this.
Second, M2.
Q1 equals minus
M2.
which one?
M2 is equal to
M2.
theta.
This is 2 theta. Yes. Correct? That's 2 theta. Now, as I did it, I can write in matrix notation the force displacement ratio. I get this stiffness matrix. There's so many different stiffness matrix. It is nothing but the matrix which relates the independent displacements with the forces. That's how I define stiffness matrix. It is the matrix which relates independent displacement with forces which need not be independent. So, when it is independent displacements are related, stiffness matrix is derived. That with respect to element stiffness matrices for a being element. Likewise, plane frame, axial force is included, that degree of freedom. So, all element stiffness matrix I have defined with respect to truss, beam, plane frame. So, it's a big thing I have done in 1 hour or so, all element stiffness matrix. And simultaneously I have told what is the difference between element and global, because loads will be global while doing the analysis, applying equilibrium conditions, we have to match with respect to the same coordinate systems. That's all. That transformation if I tell, then things are good. And of course flexibility, I have to define flexibility matrix. Of course, then once I define this independent, that is only dependent, that is only converse of this I told. So it is only inverse. That's as simple as that. That unit 2 is only this. Basic concepts of your flexibility, stiffness, local, global coordinate systems, and superposition, and all those things. If you see the syllabus, everything I am covering here. So in the next class, probably unit 2, I can just complete it. So now this, if you write it in matrix form, so write it in matrix form. So I will write corresponds to one coordinate first, that is M1, then 2, M2. So you better write it corresponding to 1, 2, 3, 4 only. Or vice versa. Accordingly, only elements will change from this. Nothing other than that. M2, then Q1, Q2, or Q1, M1, Q2, M2. Most of the books will give that Q1, M1, Q2. I'm just altering it, it doesn't matter. It's all same. Very simple, straightforward thing. So that is nothing, right? 2EL. I got here all the equations.
Three counts.
Pardon?
3 can take common. 6 here also.
Oh, okay. We'll do that. So here, M1 means theta 1. M2 means, this also recorded corresponding to that. Here, V1. Here, V2. This is the relationship between the independent displacement with the force. And that relation is my element stiffness matrix. There, AE by L, 1 minus 1. Here, let us see what we are going to get. So here, let us take 6 outside, 6 or 12. LCM I will take it 3, 2, 6. 6 if I take it outside. Also, I will take here EI by 12 EL. I will take EI by 12. Then corresponds to M1. So since this I have to multiply, only 2 is there, so this I have 6 I will take side. 6 if I take it outside. Then here I have to multiply by 12. All these things I have taken here are to avoid the confusion by it may create confusion to you. I will take only, I will retain 2EI by yellow. That is as simple as that. Let us not create problem. A very 2EI by L is there. I will take 2EI by L outside. And for M1, here it is 2 theta 1. Correct?
Yes.
So it is 2. Then theta 2, it is 1. Then this is minus 3 by L. Here it is plus 3 by L. So it has to be same. Because always the stiffness matrix is symmetrical. Always that you have to remember. All my stiffness matrix or flexibility, they are symmetrical matrices. So let us check this. This is M2. M2 2A by L. I have taken outside. So here it is theta 1 theta 1. So naturally it is 1. Then 2 theta 2. Next it is minus 3 by L. Then 3 by L. Next, Q1. This equation, Q1. It is 2A by L square. So I have taken here 2A by L. So another L has to be inside. So that means it is 3 theta 1 by L. 3 theta 1 by L. Minus 3 by L. Correct? Next, theta 2. It is again minus 3 by L. This also symmetric. Minus 3 by L. Then this is 6 by L square. Minus, this is minus, there also minus, so it is plus 6 by L square. Then it is 6 by minus 6 by L square. We do that minus 6. So here this is 6 by minus 6 by L square. You can check Q2 2EL by S by L had taken outside. So this multiplied by 1 by L. So this is 3 by L. 3 by L, that is minus 6 by L square. Then 6 by L square. Yes. So this is forces is equal to this is Km into displacements. So this is the member stiffness matrix. So you can remember for truss A by L 1 minus 1 minus 1 1 for beam element with 2 degrees of freedom, right? Numbering moments or rotations first number or remember this probably that rows or columns will be interchanged on coming. That's all. So you can remember this. It is standard. This is member stiffness matrix for any beam member. In continuous beam, for each mark these degrees of freedoms and write that member stiffness matrix, another member. Like that for all the members, you can write it and you will get total unassembled member stiffness matrix, convert it into global thing if it is required, otherwise not. That's why I have chosen already simplified by choosing the moment as the unknown forces, like that. Right? This is about member concept of stiffness, member stiffness matrix. Next class, I will derive flexibility matrix, member stiffness matrix, a member flexibility matrix. Then we will go for global derivation, from member to global, how to interconnect. So that completes unit 2, if I derive that relationship. Most probably next class, I can complete that unit 2 also. So next we will take up problems, bars, springs, beams, by flexibility as well as stiffness, nothing other than that. Simultaneously, you can use computer or write your own program using MATLAB because they are all only matrix notations. You can represent each of them by individual matrix and you can do or add or subtract using your force displacement relationship, arrive at the unknowns. That's all the basic concept of this matrix method of analysis. We'll continue with the next.